we have something straightforward like this one, 2x minus 1. So here's an equation, right? Typically, we like to write equations in x's and y's, so we start off doing this. And then the very first time you ran into these, they would kind of spell out what to do. They would say, find the value of y when x equals 5. Right? Nice long sentence like that, so it was clear what you needed to do. What you needed to do is come back up here and say y equals to 2 times, and this is where you input the 5. Let's see how this looks. Input the 5, and then minus 1, so y equals to 10 minus 1, which is equal to 9. Okay, so now we have a nice sentence. Y equals 9 when x equals to 5. Right? Pretty straightforward. Well, you know, mathematicians are lazy. We look for shortcuts, right? So rather than this whole long sentence and describing it this way, we jump next to tables. So we create a table. So rather than all this work here, we'll just create a little table where we put x's and y's. And so they might just simply say, fill out the table or something, and they might put a 5 there. So you know that that means that you got to go into here, replace the x with a 5. 10 minus 1 is 9, and you get that, right? Or some other values. How about a 0? Okay, that would be 0 minus 1, that's negative 1. How about negative 2? That becomes negative 2 minus 1 is negative 5. And so on and so forth. Good? Okay, so the important point that we have to keep in mind is that there are many answers, solutions to this equation, right? There isn't a single one. I can't just say the answer is 9. And, well, I'll say solution. Solution is 9. That doesn't mean anything. What do you mean? The solution is 9. Well, okay, I guess the solution is y equals to 9. Even that, no, what does that mean? A solution. So it's a pair. When when x is equal to 5, then y equals to 9. That's the connection we want to say, right? Okay, and so rather than writing it that way, then we can just write it as 5 comma 9. Right? That notation right there lets us know that when x is 5, y is 9. Alright, well, we want an even better notation than that, so we created function notation. So with function notation, we're going to let y equal to, f of x, and so this will be written as f of x equals to 2x minus 1. Okay? The f of x represents the y. It is together equal to that. F is not a new variable. I know we're introducing a new letter, but it's not a variable. The f is sort of the title of this equation. So that one of the advantages of function notation is that we can have lots of different equations indicated by different letters. So I'll show you that in one second. So what we want to do is we want to be able to write f of x this way. So f of 3, for instance. This means that we're going to replace each of the x's with the number that's in there. So this value in here is the value of the independent variable, in this case x. Okay, so this means x equals to 3. That's the definition of what this means. Okay, so we're going to go to our equation, which is 2 blank minus 1. And so we'll put a 3 in here, and we get 6 minus 1 is 5. And so we're able to write down the whole thing as f of 3 equals to 5. So that encapsulates the whole thing. The value of y, which is this whole statement here, f of 3 is y. The answer, the solution, the value of y is 5 when x equals to 3. So I can kind of represent them both in there. And the value of using the letter f in here is that we can use different equations for different letters for different equations. So For instance, I could have a g of x equals to x squared plus 1. Give me a number, square it, add 1, that's the g function. I can have an h function. H of x says x minus 2 divided by x plus 1. Give me a number, I'm going to subtract 1 from it and then divide it by that number plus 1. Right? I could have a w function. W of x equals to x minus 2. Right? Okay, so then I can refer to each of those equations by this front letter. So it's not a variable, it's the title of the equation. So I could say something like find g of 7. Okay, g of 7 means it's this one. It's the g function, and the instructions are take the x value, which is 7, square it, and then add 1. 49 plus 1 is 50, so I know that g of 7 equals to 50. Any questions? No? I can ask about the w function. W of 10. W of 10, I know it's not this one, it's not that one, it's got to be that one because of the w. That's part of its name, it's its title. So w of 10 is 10 minus 2, which is 8. So I'd write w of 10 equals to 8. Okay? So again, it's not a variable. You don't solve for it. The most common mistake people do is that they next try and divide both sides by 10, and they get this. W equals to 8 over 10. That doesn't mean anything. Okay? W is not a variable. It's the title of that function over there. You never solve for it by this way. Okay? So you would never divide this way and divide that. Doesn't mean anything. You stop there. This is letting me know that if I go over to the w function and I let x equal to 10, the answer is going to be an 8. Good? Questions? We're good, 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 good? Okay, so that's function notation. Well, now that we know the notation, well, what is it? So, let's look at a couple of situations. So as I said in this class, we do a lot of word problems, a lot of real-world situations. So we'll be dealing with a lot of cases where we have to translate some sort of real-world situation into some sort of a graph or a grid. And so let's look at a couple of things. How about if I do the following? Let's say I decide I'm going to do a study. And what I'm going to do is I'm going to go to each one of the classrooms in this building. And I'm going to count how many students are in there. And then I'm also going to figure out how many parking spaces were taken up by the people in that room. So that I kind of want to get an estimate of whether or not we have a parking problem. Right? So there's about 30 of you guys in here. If each of you drove your own car and parked your own car, then we needed 30 spots. But not all of you guys drove. Some of you guys walked. If you live close enough to school, or you got dropped off, or you used public transportation, or you used a variety of different options. Maybe bicycle. Maybe you drove, but then someone took your car. You got dropped. Like swapped, or you're sharing a car or something like that. So what are the possible kind of results that I can get? So I'm going to define, as I defined it, I want to be able to graph my possible results. So I'm going to go to all these different classrooms, and I'm going to, first of all, count how many students are in that room. So in this direction, I'm going to call this n, where n is equal to the number of students in room. Okay? And I'm going to call this p to represent the parking spaces. So number of parking spots used. Number of parking spots used by those students. Okay, so based on what I'm trying to work with here, is it possible, let's say I have 5, 10, 25, 30, 25, 20. So let's say this is 5, 10, 15, 20, 25, 30, 35, 40. Let's say we have that. And let's say same in this direction, 5, 10, 15, 20, 25, 30, 35, 40. 5, 10, 15, 20, 25, 30, 35, 40. Okay, so based on my real world situation, is this possible right there? What does that dot represent? I went to some classroom and I walked into some random classroom in this building and 20 Care Bears, 20 Snickers bars, 20 students. There were 20 students in that classroom and 10 parking spots. Is that a valid answer? Could that happen?
Yeah.
Yeah. Okay, well what about the other 10 people? What happened to them? I don't know, they didn't use a parking spot. Maybe they were dropped off, maybe they walked to school, maybe they used public transportation, I don't know. They just didn't use a parking spot. Okay? Alright, what about this one? Is this a valid possible answer?
No.
5 students in that classroom and they took up 25 parking spaces. Probably not, right? Unless they're all driving like 18-wheelers and they like parked and like took up a bunch of spots in each one. It seems unlike, no, this is not right. Okay, so there are some things that make sense in this word problem, in this situation, and some things that don't. So, what about this? Is that a valid thing? What does this mean? This one down here says, I went to some classroom.
20 students.
There were 20 students, and they only took up 5 spots.
Yeah.
And then I went to a different classroom, and they took up 10 spots. So it's possible there could be 2 different classrooms that have the same number of students, however, they take up different numbers of spots. Right? So as I go through and I come up with different values, maybe I get, oops, that one's not good. How about this one? And then maybe over here I get like that one. Okay, are decimal values allowed here? Can I have 20.2 students?
No.
No. Can I have decimals in this direction? Can I have 5.6 parking spots?
No.
Probably not. I guess it depends on, like you said, like maybe it takes up more than, no, that's probably not true. So, counting numbers make sense in this word problem. Good? Okay. So, here is one graph, right? The graph is a bunch of dots. We'll look into more precise definitions of those in a little bit. So here's one case where we have a connection, right? Each one of these little dots here is a connection between a value in this direction, the independent variable, right? This one's the independent. That makes this one up here the dependent. We also like to refer to it as the input value. The input value, which makes this up here the output value. Okay, so certain things make sense in this situation and certain things don't make sense. We can look at another situation. How about if I wanted to gauge the stress levels of students? So I asked people, I'm going to take a sample, a random sample of 10 students. I'm going to randomly select 10 students each week of the semester. So week 0, the beginning of the semester, week 1, week 2, week 3. Each week, I'm going to take 10 randomly selected students and I'm going to ask them to self-diagnose their stress levels on a scale of -10 to positive 10 and 0 in the middle, where -10 means no stress at all. Everything's great. No stress at all. Where this is very high stress. Very high stress. And this is 0, just means normal. Whatever normal is for them, we're just asking them to self-diagnose. I feel like a normal Tuesday, just every day. Where this is super relaxed. I'm just totally mellowed out, relaxed. Where this is really, really, really stressed over here. So you ask 10 people to self-diagnose, how do you feel today? And then I'm going to add up all those scores, 10 randomly selected students, and then I'm going to record that value. And I'm going to do that 1 time per week for the entire semester so I can see what kind of results I get. Right? That's what I've described I want to do. So let's look at the possible, one possible set of values, or what kind of values we can possibly get. So in this direction, we're going to have weeks, put W for weeks, week number in the semester. So for instance, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Week number 1, week number 2, week number 3, 4, 5, 6, so on and so forth, right? And then I think there's 16 or 17, well, let's say 16 weeks in the semester. So it wouldn't make sense to have week 17 or 18, 19, in this case, the way I've described it, right? What about in this direction? What's the smallest possible value we can get? I'm grabbing 10 scores from people and I'm adding them. So what if, let's say, well, the highest, what's the most we can get? What if all 10 people said, I'm super stressed? Then I would get 10 plus 10 plus 10, right? So the biggest value I can get is like 100 up there, super high stress. Or the other direction, maybe in this case, negatives are valid. Maybe all 10 people are super relaxed, no stress at all. Maybe I get a negative 100 as my answer. Or any variety of results in the middle of those. Okay? So, based on what I've given you, is this a possible answer? A dot right there. Could that happen?
Yeah.
1 comma 0. Is that something that could happen? It means that week 1, all people said 0?
Normal.
Okay, all people said normal? Is that what that means?
Yeah. 1.
Remember, I'm adding them. So is it possible that exactly 5 of them said 10 and exactly 5 of them said negative 10?
Yeah.
So that when I added them, it was just 0? Okay, so that doesn't mean that all of them said 0. It's that when I added them together, I got an answer of 0. Okay, so maybe that's what happened one week. Is this possible? Can I have that? Week 1, I got a 0, but I also got a 25.
No.
Not the way I've described it. I mean, there might be some other scenario out there where that's allowed, but the way I've described it, I said each week I'm going to get one group of 10 students randomly selected. I'm going to get their stress level. So I should have 1 dot above each one of these numbers, right? This is okay, maybe this is okay, maybe this is okay. Exactly 1 dot above each one of these numbers. Okay? If one of them is missing, how would you interpret that when you're looking at that? What happened there? You just didn't take a score that week, right? Maybe you were sick, you forgot, whatever. There is no score that week. Could happen, right? As you're interpreting this data. Good? Okay, well, we could change it. It doesn't have, oh, one more thing. Do they have to be integer values? Can I get decimals in this direction? Well, I mean, I just said rate your score. It's possible someone gives me a decimal answer, right? I feel like a 3.2 today. All right, that's how you feel, all right? So, you know, whatever answers you get, it's what you get. So it's possible to get decimal values here as well. But we can't get any decimal values this way. That doesn't make sense in terms of this word problem, right? Because you can't have, we're not going to do week 1.2. No, we're going to do once a week. Week 1, week 2, week 3. So just the way I've worded it, it entirely depends on the way I phrased it. Good? Everyone clear? We could change the way I phrased it. I could say every week I'm going to grab several groups. Each group of 10 people. Week 1, I might have this group, I might have another group, and the sum of their stress levels was 25. Week 1, maybe I have another one, and their sum of their stress levels was negative 53. I mean, I don't know, there could be lots of them. So in another kind of situation, it might be valid to have lots of dots above each one of these numbers to indicate that there were lots of groups. This week 4, I did 1, 2, 3, 4, 5 groups that week. This week I did no groups. This week I only did 1 group. This week I did 3 groups. Right? It could happen. Right? So we have to adjust what we graph to fit the word problem or what we're trying to accomplish. Or the other way around, we have to be able to look at our graph and be able to interpret it properly. Good? And again, these dots should be thought of as a connection between a value in this direction, the independent variable, and a value in this direction, the dependent variable. Okay? So we refer to these values that we're actually using as the domain and these as the range. We'll get into that a little bit more in a second. Any questions so far? No. One last one. So let's say that we are going to look at the distance a student is away from their house in a 24-hour period. So let's say we start off at 4 a.m. right there, and then that's going to be, let's say 6, 8, 10, noon. So that's 6 a.m., 8 a.m., 10 a.m., noon, then 2, 4, 6, 8, 10, midnight. Midnight. And then 2 and 4 a.m. Okay, so we'll let that be t. T is equal to the number of, the time past 4 a.m. And in this direction, let's look at distance away from home. In miles, let's say. In miles. So 1, 2, 3, 4, 5, 6, 7, 8. Let's say it looks like this. And let's use the letter D to represent that. So we got T and we got T and we got D. So one possible graph, for instance, could start there and do that. What is this describing? What's happening right there? If this is the way the picture looked.
He left.
He started off at 4 a.m. He was
Leaving.
at home, right? He was 0 distance away from home. He was at home. And he was leaving home. He's getting farther and farther away from home. Good? Alright, so what if he wasn't there? What if the graph started out there? Is that a valid thing?
Yeah.
That means that he started off his day 2 miles away from home. Okay? If it looks like this, what does that mean?
He stayed there.
He was there, he wasn't leaving, he wasn't moving, right? He's in some other location, not at home. That location is 2 miles away from home, and he was there from 4 a.m. to 6 a.m. Right, he didn't leave. Okay, then maybe it looks something like this. Maybe something like that. Maybe something like that, something like that, something like that, maybe like that, then like that, then like that, then like that. Alright, so he's in some location 2 miles away from home. He stayed there for 2 hours. Okay, then what happened? At 6 a.m., started going home, right? He's traveling home. He's getting closer and closer to home, closer and closer to home. He made it home. From that point to this point right there, what's happening?
He stayed home.
He stayed home until there. Then he left. He's heading farther away, and then he's getting closer to home, and then maybe he arrives somewhere. So this part right here, maybe he's heading there. He's heading someplace that's only 1 mile away from home. But because of streets and freeways and traffic and all that, maybe the fastest way to get to his destination involves going farther away than you need to, and then eventually going to where you need to go. Right, does that make sense? Sometimes the fastest way to go to that location over there is to start off going that way. Just go that way for a little bit, hit the freeway, and boom, you're there real quick. But, as far as distance goes, sometimes you go farther away than you need to, and then you go back to where you wanted. Alright, so then he stayed in one spot for a little bit. Then he started driving again, and he was getting farther and farther away from home, farther and farther. Then a little closer to home, but then okay. And then he was stationary again from there to there. Right, so he's in one spot, not moving. Then he's again getting farther and farther away from home, a little closer to home, a little closer to home, and then he reaches some destination and he stays there. That's what we got. Any questions about reading this graph? No? So like let's say from A to B, he was stationary in one place, wasn't moving, he was exactly 2 miles away from home. From B to C, he was heading home. C to D, he was at home, he wasn't moving. From D to, say, E, he was at first getting farther and farther and farther, and then a little closer to home, and then eventually reached some value E. where he stayed from E to F, he didn't move. Then he traveled again, he was moving, he was getting farther and farther away from home, farther and farther. Then he started getting just a little bit closer to home until he arrived at some place G. He stayed there until H, right? So in that time frame, from this point in time to this point in time, he was stationary at about 3 miles away from home. And then he decided to travel, initially getting farther away from home, then coming back until he reached some destination I, and then he stayed there the rest of the time, and we go back to finish our 24-hour period at exactly 4 a.m. Good. Did he finish in the same place he started off the day?
Oh, looks like it.
It's hard to tell with my thing, right? But if this was a height of 2, then that would guarantee?
Yeah.
Well, okay, first of all, if this was not, like if I could trace it all the way back, if I could go all the way over here, and I would say, oh no, look, it's at 2.5. If this is 2.5 height, does that let me know whether he ended, can I answer that question? He ended in the same place that he started?
He didn't.
He did not. Good?
Yeah.
Does that make sense? If this had a height of, if I could trace it back, if I could get a more precise answer here, and look, it's at 2.5. Oh, I can definitely answer that. No, he did not end in the same place where he started off his day. All right, but what if I did trace it back and it did go back to 2? It's got a height of 2. Can I answer that question? Yes, he did. Are we sure?
It could be on the same distance, but...
All we know for sure is that he ended his day 2 miles away from home, and he started his day 2 miles away from home. That doesn't guarantee that it's in the same spot. Maybe he's got a friend in that direction that's 2 miles away from home, and he spent the night there. That's where he started off his day. And he's got a separate friend exactly 2 miles in the other direction away from home. Right? Direction is always positive, away from home. It could have been a different place. So that doesn't necessarily guarantee. Okay, so we know the real world situation that we are describing. We have a one potential answer for it. And there are things that make sense within the framework of our word problem and things that don't make sense. So for instance, is it possible that as he's driving and doing his distance away from home, that this thing goes down here? Is it possible that this goes below the horizontal axis?
No.
Distance could never be negative, right? So we can't be negative 2 miles away from home. That doesn't make any sense, right? Distance is always positive. And a direction, right? Like, the Staples Center is that way. The Staples Center is 7 miles that way. You never say negative 7 miles. Staples Center is negative 7 miles that way. Do you mean that way? What do you mean negative 7 miles? So direction, right? Distance is always a positive thing. So we can't really graph a negative. It doesn't make sense here. All right, is it possible that there would be a situation like this? There's some point there where we have 2 dots on top of each other. Is that possible? Is that ever going to happen?
No.
Can't be in 2 places.
You can't be in 2 places at once, right? So there's no way that this graph could ever split off and do something like that. He was there and then he went to do 2 different places. You're never going to have, in this situation, cases where one is on top of the other this way. Make sense? Okay. What about the values? Are these only integer values, like in the other cases? Can I only have 6 a.m., 8 a.m., 10 a.m.?
No.
Can I have decimal values?
Yeah.
Yeah, an hour and a half, right? We can get very precise if we want to. 1 hour, 31 minutes, 16 seconds, 14, right? So we can get as precise as our technology will allow us, but any decimal value is valid along this direction. Okay, so some things make sense, right? An open hole doesn't make sense. That means you've disappeared completely. Splitting off this way doesn't make sense. Having one on top of the other doesn't make sense. You can't be in 2 places at once in one particular value. So different situations have, different things that make sense. So we have to be careful about the word problem and, how to interpret it in the graph, and then again, how to interpret the graph into the word problem back again. Okay, but in general, when we begin, or in general, we like to think about graphs that don't have a word problem associated them to begin with. So we just generally have an x-axis or horizontal axis and don't think about applying time or the number of students or the number of parking spaces. None of that. We just think of it in general. So as a very general description of what we're going to be working with, we're just going to have values in the input direction, the horizontal direction, connected, related to values in the vertical direction, which is the dependent variable. Okay? So when we have that, we have relations. A relation is a set of ordered pairs. The domain of a relation is the set of all values in the independent variable, and the range of the relation is the set of all values in the dependent variable. So again, this is a very generic description of relations, and we have all kinds of situations we just looked at. So here, where we're looking at the distance away from home, the time in a 24-hour period, then all of these numbers here are part of our domain. They're possible input values. So from 4 a.m. Over to 4 a.m., the 24-hour period is our domain. We can also describe the range. The range is all possible distances away from home that we get from here. So if this was the answer that I got, then these right here are the possible answers. At one point I was at 0 miles away from home. I would look for the biggest value that I got, which would be maybe that one. Let's say that one is the biggest result I got, which makes it 3, 4, 5. So if this was 5, then between 0 and 5 is our range. Any value between 0 and 1 was reached at least once during this 24-hour period. Good? 6 was not. I was never, if this is the answer, I was never 6 miles away from home during this particular 24-hour period. Does that make sense? Sort of? So in general, each member of the domain is an input value. Each member of the range is an output. So we like to think of it as input-output pairs. Here's another example. So if we had this table, 3, 4, 5, 5, and 2, 1, 3, 4, then these are ordered pairs. We can graph them this way. And we'd have this little grid here with these 4 ordered pairs. And so this is a general grid. We don't have a word problem associated, but I mean, you could think of something. Maybe the X is number of students, the Y is, whatever, number of teachers, and I don't know, there could be some word problem where this is the answer. And in that word problem, maybe this makes sense. Maybe there is some reason for why 5, 4 and 5, 3 are 2 separate answers, and it makes sense in the word problem. So sometimes you're allowed to stack them one on top of the other. The way we were able to do that in the previous one that we did. Right? In this case, the number of parking spots, I went to a room, there were 20 students, those 20 students used 5 parking spots. I went to a room, a different room, there were 20 students and 10 parking spots. Okay, so in some cases this makes sense, some cases it doesn't make sense, right? Okay, so in general we can graph them this way. We also like to think about this input-output machine, where we're inputting the value of 3, for instance, and the result is 2. Now, how did we get that result? Well, some sort of relation happened there in that giant rectangle there. Something occurred. It could have been an algebraic thing, like maybe we took the 3 and we squared it and divided it and took the root of it and then added 7, and we did something algebraic to it, and that's how we got the 2. And then we did the same rule to 4. We squared it and divided it and took the root and then divided, and then that's how we got the 1. So there could be an equation that describes the relation. That's possible. Or maybe the relation is simply a picture. There could be a word problem, a situation that describes how 4 was connected to 1. Right? So you can describe that relation with an equation, an algebraic equation. You can describe it with a graph to show how they're connected or which one's connected to who. Or it could be some sort of word situation where you verbally describe how things are connected to each other. Okay? But in a relation, there's really no restrictions at all about the connections you make between the inputs and the outputs. No restrictions at all. Any input could be connected to any output. And so 5 can be connected to 3, and 5 can be connected to 4 as well. That's in a relation. Everything is allowed. In particular, we want to focus our attention on a special kind of relation, which is what a function is. A function is a relation where we don't allow that particular thing right there. 5 connected to 3 and 4 is not allowed in a function. Each input value is connected to one output value. That's a function. Okay? So, a function is a relation in which each input leads to exactly one output. So here we have a problem. 20 is connected to 5 and 20 is connected to 10. This is not a function, the way I've written it, the way it is. It's a valid mathematical situation. You might have to study these kinds of things, but not in this class. In this class, we focus on functions. This is not a function. We really don't deal too much with these. Every once in a while, but for a variety of reasons, we focus our attention on functions to begin with. Okay? The one with the distance, we established that some things just don't make sense. Right? So let me get rid of this thing. We established that having a hole like that doesn't make sense. So there wouldn't really be a hole. And we established that splitting off like that doesn't make sense. Or even just having a single dot above just doesn't make sense either. You can't be in two places at once. So this one is the graph of a function. For every input, there is exactly one output. Good? Every input, every value in the independent axes has exactly one unique value in the output. Notice that there are some cases where there's a lot of different inputs that all lead to the same output. Right? Like when they're stationary. Like at the beginning from 4 a.m. to 6 a.m., they didn't move. So all these input values, 4 a.m., 4:01, 4:05, they all lead to 2. They all lead to 2. They all give you the same value of y. That's okay. You're allowed to repeat this, but you're not allowed to have one value in this direction lead to more than one value in that direction. Okay? Good? Good? Okay, so that's what a function is. We can describe functions with tables and equations and graphs. We often use this notation as well, which we have to look at because the book has it sometimes. And it's these jelly bean looking things. So for instance, we could describe a function this way. Y equals to double x plus 1. So that's an equation. We can rewrite it as a function notation as 2x plus 1. Okay? So this is saying that you give me an input, I'm going to double it and add 1 to it. Double the input, add 1. That's what that's letting me know. Okay, so I could describe this in this sort of way, where I have the domain of my function, domain of f, and then over here I have the range of f. And so I could make connections like the number 3 is in there, and the number 3 leads to what? 7. So this picture is letting me know that 3 is connected to 7. It's mapping to 7, right? Because I double it and add 1, I get to 7. Or 5, double it, add 1, gets to 11. Good. Or I could just kind of write down the equation that would give you the answer. Like let's say I put a 7 in here. Then instead of putting 15, I could put 2 times 7 plus 1. You know, kind of make you do the work. That's valid too. Good? Good, good. Or I could use a letter. So I could put like a letter A. So what happens with A? Well, I don't have like a number answer, but just like up here, I can describe for you how you would get the answer. All you have to do is replace your number A right in there, so you would get to 2A plus 1. Good? You're good? Okay, so it just describes the function that way. So this is the function going in that direction, from here to there. This is the set of domain values. This is the set of range values. So it could look something like that. The A leads to f of A. Of course, x leads to f of x. So it goes from the domain to the range. Okay, so the purple looking one, all the numbers in there are the domain. Sometimes there's very specific ones, like these are it. There's only 3 numbers, that's the domain, these 3 numbers. There's only, these values right here in my, that's it, that's my range. And sometimes they're just representative of a larger set, right? It might be all counting numbers, or it might be all real numbers. The word problem, hopefully the exercise you're on, should make it clear whether they mean all numbers and these are just some representative values of those numbers, or if they specifically mean these are the only 3 in my word situation. These are the only 3 values in our domain, right? So it could be both cases. All right, considerations. Is this the graph of a function, y equals to x plus 2? Well, if I graphed it, it would look like a line, right? We know that because, well, this chapter only deals with lines, so that's one good way to know. Also, it fits the form of y equals mx plus b, where the m is the slope, and it's what in this case? 1. And the y-intercept is 0, 2. Okay, so if I wanted to do like a quick little sketch of that, here is y, here is x, it's 0, 2, right? 0, 2, and then it goes out 1 and up 1, since the slope is 1. Slope is 1 over 1, which is rise over run. So 1 unit that way, 1 unit up. We get to another point, we draw the line that connects them, and we get to that line right there. Okay? So, is this the graph of a function? Remember, the only thing we have to make sure is that each input leads to exactly one output. So, is this going to be the graph of a function?
Yeah.
Yeah, that's always the case. In all lines, there's only one exception, right? What kind of a line would fail that? A vertical line, right? So what we're really looking for is to make sure that there's never a case where 2 dots are stacked right on top of each other, right? And they come from some same value of x. We never want to have that for functions. Good? So all lines are going to be functions, with the only exception being vertical lines, because obviously they fail that test. All the dots are stacked on top of each other. Good? Questions, questions, questions? Okay, so if we have a picture, if we have a graph, and we try to determine if it's the graph of a function, that leads us to something we call the vertical line test. All we have to do is kind of sweep this imaginary line across our graph, and if it ever touches our imaginary vertical line at more than one point, then we know that there's going to be a case where one x value leads to 2 y values, and we know that that is no longer the graph of a function. Right? So for instance, if I gave you this picture, say I gave you that picture, is that the graph of a function? As I sweep my vertical line across, is it ever going to touch at more than one point at the same time? No. So this is the graph of a function. Good. So this is the graph of a function. What about something that does this? It's not a function because, okay, we're good here. It only touches at one point, only touches at one point, only touches... we have problems. For instance, right there and right there, these 2 points are right on top of each other, and they're connected to that point on the x-axis. There is some value a along the x-axis that leads to some value b and some value c. We have a problem, right? There is at least one point along the domain that leads to more than one value along the range, not the graph of a function. Okay, so the vertical line test, we sweep across and we, if we sweep this line across, if it ever touches more than one, then it is not the graph of a function. Moving on, how about this thing? What about this thing? Y squared equals to x. Is that a function? Okay, so we have to think about this. We have y squared equals to x. So consider this. Consider this. If x is equal to 9, what are we going to get? Y squared equals 9. something squared equals to 9. What can I stick in that something?
3.
3. 3 squared equals 9, right? So I can put a 3 in there. Is that the only thing I can put in there and make it a true statement? What about negative 3?
Yes.
Yeah. Negative 3 is also an answer. Negative 3 squared is 9. Positive 3 squared is 9. So when x is 9, there are two possible values of y. We do have a case where one is stacked on top of the other. If we graph them, they would look well, no. Let's do that. If we graph them, they would look a little like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here's 9 along the x-axis. And 1, 2, 3, 4, 5. 1, 2, 3, 4. So we end up with something that looks like this. 9, comma 3, 9, comma negative 3. Right? So we have a case where the two dots are on top of each other. Right? This is a case where this is not going to pass the vertical line test. This is not a function. Good? There's many other cases out there. What if x was equal to 4? If x was equal to 4, then y could be 2 or negative 2. So there's a lot of different situations where we would notice that one input value leads to 2 or more output values. It's no longer the graph of a function. Good? Any questions? Questions? No? Okay. So vertical line test. Back to vertical lines. Is the circle the graph of a function?
No.
No. If we sweep a line through it, it's going to touch it more than one spot, so it is not the graph of a function. What about number 2? If we sweep a line through it, it's not going to touch it more than one spot at the same time, so it is the graph of a function. Okay? So the first one, if we sweep a line, it touches at more than one spot, so it is not a function, not the graph of a function. The second one, as we sweep through it, it only touches at a maximum of 1 point, so it is the graph of a function. Good. What about that guy? Is that the graph of a function?
Yeah.
Yes, function. What about that one?
No.
No. What about that one?
Yeah.
Yes. Okay. Alright, that one. Okay. So we can express functions in 4 ways. We talked about an equation, right? So we can have something really straightforward like y equals 2x plus 1. That's an equation. It's a function. Every input leads to exactly one output. So it is a function. We can describe it with a table, right? Once we put some values together, we can describe this as negative 1 is negative 1. 0 is 1, and 1 is 3, and 2 is 5. Right, so we can describe it with a table. We can also graph this, right, and describe it with this graph. It's got a y-intercept of 0, 2, 1, 1. I don't know, something like that. Where this is 0, 1, and 1, 3. Well, you can always add more detail, but you can describe it with a graph, an equation, a table, or with words. You could say it's twice the input plus 1, or double the input plus 1, or 1 more than twice the input. There's all kinds of ways in which you can describe this, including using the language of input-output. Or there might be some real-world situation where maybe your salary, your paycheck is equal to number of hours worked times 2 plus 1, I don't know, something along those lines. So there might be some meaningful reason for what the x and the y are in a particular situation, or it could just be some sort of general application where you just leave it in terms of x and y, or input, output. Okay, so we got equations, we got tables, we got graphs, we got words. Those are the things we deal with functions. And then another important thing we do with that we're going to be doing in this section is finding the domain in the range. So the domain is the set of all input values that are valid for a particular function. and the range is the set of all output values that are valid for a particular function. So one of the things that you'll be asked to do is that you'll be given a graph and you'll be asked to find the domain and range from the graph. So to find the domain of a function from its graph, look at all the points on the x-axis that correspond to points on the graph, all the points that are valid for that particular graph. To find the range of a function from its graph, look at all the outputs on the y-axis that correspond to points on the graph. So consider this. So if the red function there is our graph, it's our function, then to find the domain, we think of like the shadow down on the x-axis. All those values in that blue region on the x-axis are valid input values of that function. I can trace them back up to the red function and find a result. So that's the domain. And the range is all the possible outputs that you get when you input all the values on from that domain. So the purple region over there is our range for this particular function. I like to think of it as squashing it. So if you take the red function and you squash it this way along the x-axis, everywhere the red touches is the domain. So you can imagine if there was like a hole in the red function, if there was like a hole somewhere and you squashed it down, then maybe there might be like a little hole in the domain. There might be some value in the domain that doesn't have an answer. But in this case, it's nice and smooth and solid in between those in that little segment. So you squash it down, the domain is the entire blue region. The range, if you squash it this way along the y-axis, everywhere it touches is the range. So you squash it this way, everywhere it touches. Good? So something with some numbers. Consider this one. Right, so it's like a little half circle, right? And if we squash it this way along the x-axis, everywhere it touches along the x-axis is the domain. So it goes from -2 to +2. It touches everything between -2 and +2. If we squash it this way, from 0 to 2, right? It touches everything from 0 to 2, so that's the range. Notice the brackets. The brackets indicate that we include the endpoints. So the notation of bracket -2 comma 2 bracket is indicating that it's every single number between -2 and +2 and including the endpoints. That's what those brackets represent. Same thing with the 0 comma 2. We go from 0 to +2 and we include the endpoints, so we put brackets on there. Any questions? No? Okay. So what about this one? So we have this given function, find the domain. If we squash it this way, everywhere it touches is going to be the domain. So from 2 to 1, and we include the endpoints because we have solid dots at the ends, so we want to include the endpoints. So we put brackets, right? So -2 comma 1 with brackets around it would be the domain. What about the range? From, what's the smallest? Okay, I'm sorry, did I say the range? The range going this way, squash it this way, everywhere it touches, the smallest value that it touches is 0 to 3. From 0 to 3, do we include the endpoints? We do. 0 to 3 is the range with brackets around the end. So there we go. Okay. What about this one? So what's the domain? Squash it this way. From -2 to +1. But we do not include -2. It's got that little open circle at the end there. That means we don't include that endpoint. So we want to include all the points between -2 and +1, including 1, but not including -2. We get infinitely close to -2 from the right-hand side, like -1.9999999 is in there, but -2 is not. Okay? So it's going to be parentheses. When we don't want to include the endpoint, we use parentheses in our notation. So it's going to be parentheses, -2 comma 1 brackets. So, like that. -2 comma 1 brackets. That's the domain. Okay? Now the range, we squash it this way. Everywhere it touches along the y-axis is the range. So the smallest value is -1 to +2. Right, that's the range. We do include the -1, so it's going to be brackets, -1 comma +2 parentheses, right? Because we don't include the 2. So that. Good? Questions? Okay. What about these? What's the one, what about this one? The domain for the first one? -4 to +5. Good. We include the endpoints. What about the range? -3 to +4. Good. A very common mistake is people think it's from -3 to +2 because they're just looking at the endpoints. And that's not what we want. We want all possible y values. So if you squash it this way, everywhere it touches everywhere from -3 to +4. And we put brackets around those to show that it's we include the endpoints. What about number 2 here? What's the domain? Those little arrows indicate there's a pattern, right? It keeps growing in that direction. It keeps going on forever. So, you know, if you kind of zoom out, those things are going to keep growing. So all of it, if I squash it this way, it's going to touch everywhere along the x-axis, right? Okay, so it's going to be all numbers. You can write down all real numbers. You can write down all real numbers like that. We also like to use this symbol to represent that, all real numbers. But more commonly we use this notation for this purpose. So we want to go from -infinity to +infinity. Domain. Right? You can write it in any one of those ways. They're all good. Right? But this is probably the most common one, right? So from -infinity to +infinity. Don't make this mistake. We never ever include a bracket when we're dealing with infinity, right? So we can't include the actual infinity since it's not a number we can include. It's more of a direction or a concept. We go that way. So we get infinitely close. We keep going that way. So we use parentheses always with the infinities. Okay, what about the range? So now we squash it this way. Everywhere it touches is the range. What's the smallest value? -3 and all the way up to infinity. So -3 to infinity. Bracket there, because we do include the -3, parentheses there. This is our range. Okay, good? Questions? Another way of saying it is just all numbers greater than -3. That's another way of expressing. Good. So we got that. Okay, another thing we'll be asked to do is to find the x and y intercepts from a graph. Easiest thing in this class. So to find the x-intercepts, look at the points which the graph crosses the x-axis. That's the very definition of the x-intercepts. Just keep in mind that in this book, we often use different letters, so it's not always the x-intercept, it's the horizontal intercept, which might be the w-intercept or the p-intercept. It depends on whatever variable we're using in that particular context. But in general, we usually use x's and y's, so we often refer to it as the x-intercept. So we look at the place where the graph crosses the x-axis. To find the y-intercept, we look at the point, look for the point at which the graph crosses the y-axis. So we have some picture, some graph, we figure out where it crosses, it's all good. A function can have more than one x-intercept, but at most one y-intercept. Why is that? Okay, what's the one and only rule we have to keep in mind when we're dealing with functions? You're not allowed to have one x value lead to two y values. Okay, so if it did have two y-intercepts, that would mean that the value x equals to 0 is leading to two different places. Right? So it fails to be a function at that point. So the very fact that it's a function means it can only cross the y-axis one time. Good? But it can wiggle up and down along the x-axis and have lots of x-intercept points. For example, consider this one. Right? If we think about the vertical line test sweeping through it, it passes the vertical line test, right? That imaginary line sweeping through it only touches the graph at one point at a time. So it is the graph of a function. If we want to find all the x-intercept points, we got 1, 2, we got 3 places where it crosses the x-axis, right? So there are 3 separate x-intercept points. There's only 1 y-intercept point. So the x-intercept points are, starting from the left, -3, 0, -1, 0, and 2, 0. Yes? Okay, and then what's the one and only y-intercept? 0, -6, right? So remember to put it in as a point, as an ordered pair if you're asked this on a test. So -6 is not the answer, it's 0, -6. Good? Questions, comments, issues?